Okay, today's lesson is going to begin talking about cell notations. Uh, and the abbreviated cell notation is a way of describing an electrochemical reaction in a very shorthand way, sort of like a balanced equation describes a chemical reaction. Well, this one abbreviates that even further when we're talking about oxidation reduction, or what we call redox reactions. Now, we're going to have a cell notation that has a middle part. Generally, that middle part will be two diagonal lines, and I'll tell you about that in a moment. But then the part of the equation that is to the right of that is the reduction half cell. If you have species that are in the same phase, and so what we're looking at, say on the right, is we're looking at the reduction half cell, and if it has things in it that are in the same phase, you separate them from each other with a period. You use a single slash mark to separate things that are in different phases. So for example, if I had zinc in the presence of zinc ion, zinc metal and zinc ion would be separated by a diagonal. If I had a reaction that had oxygen and hydrogen gases in the same side of the equation, those components would be separated with a period. So you use the period if the things on that in that same half reaction are in the same phase. You use a diagonal if they're in different phases. Now here's the double diagonal line we talked about. In the vernacular, this would be slash slash. That represents the salt bridge or something equivalent to it. Remember, the redox reactions, electrochemical reactions, are typically spontaneous. And so the oxidative half cell and the reductive half cell must be physically separated in space. And we can do that by putting each of them in separate beakers and then attaching a salt bridge. Generally, it's potassium chloride gel in a glass tube. In your lab experiment, if you did that one this time, it was a piece of saturated salt water solution on a paper towel or something like that we did it in lab. Filter paper, I guess it was, little strips of filter paper. Now, in any electrochemical cell, there has to be a connection to the outside world, which has to be a conductor. Typically, it's a metal, and often the metal may be something that is involved in that oxidative half cell or reductive half cell. And that would come out of the beaker and would be the place where you would attach a wire. If one of the half cells only has things like aqueous components or gases especially, then you need an electrode for that cell that it will not participate in the reaction itself. And the element that we use is platinum. It's quite expensive, of course, but it's also very, very unreactive toward about everything. It doesn't oxidize easily, doesn't form an oxide coating on it. It is a really excellent electrical conductor. So if you've got a cell that just say involves gases involved in that half cell, then you would put a platinum electrode perhaps over there and allow the gases in and out around that platinum electrode, and it would be the electrical conductor to the outside. So you got to remember, every electrochemical reaction has to have a pair of electrodes. It has to have two, one for the oxidative cell, one for the reductive cell. one for the cathode and one for the anode. Now let's look at some examples. Here is as an example written in abbreviated cell notation for the reaction between copper and its ion and silver and its ion. The copper ion is +2. So the cell that is going to be spontaneous would be the one where the copper plus the silver ion goes to silver plus copper ion. So the copper is going to come from the copper electrode. And so the copper and the copper ion would be in that cell. In that reaction, copper is being oxidized. So that puts it on the left side of our double yellow line. And let's see, I'm trying to get a highlighter here so that I can make that a little more obvious to you. So here's the double hash line. We've got copper as a solid. It's in a different phase from copper aqueous, so it's separated by a diagonal line. The silver ion is being reduced in the reaction, so it belongs on the right-hand side of this double arrow. And it is shown as reduction. And so I would write them like this, going left to right. Copper is going to copper +2, that's oxidation. Silver ion is going from +1 to 0, so that's reduction. The silver ion aqueous is in a different phase than the silver metal, so they're separated by this diagonal line. So here are this is the overall reaction, and I've color-coded the reduction part in sort of orange and the oxidation part in blue so that you can see it. The voltage now is going to be the voltage for the copper ion is -0.337 when copper goes from copper to copper +2. When silver goes from silver ion to silver metal, it's at +0.77 volts. So this reaction, written as it is here, gives me an overall voltage of 0.433. This is for the standard state cell. Now let's remember what we talked about a long time ago about standard states. The metals, their elements, they're in their natural native state. So their oxidation numbers are 0. And in the ion, for example, copper goes to +2 and silver ion would be reduced to silver metal in this reaction. The voltage, though, that is generated is assuming you have some copper in the presence of copper +2 at 1 mole per liter concentration. And you have to have the silver ion at 1 mole per liter concentration. So this voltage is only the voltage if you set those concentrations. So just like we said before, a standard enthalpy of formation, a standard entropy of reaction, a standard free energy of reaction, a standard voltage. All of those are for a particular set of concentrations. Gases are always at 1 atmosphere pressure for each gas. Concentrations are always at 1 mole per liter for each ion that's dissolved. So this is the voltage you would generate with copper in a solution of copper +2 at 1 mole per liter copper +2, and connected through a salt bridge to another electrode made of silver metal with the solution at a concentration of silver +1 of 1 mole per liter. That will generate 0.433 volts. It's positive. A positive voltage means it is spontaneous in the direction we've got it written at these concentrations. Now let me see if you remember something. What if I increase the concentration of copper plus 2 ion? It's a product. What would that do to the reaction according to Le Chatelier? It would send the reaction back in the other direction. So if it's going to send the direction in the other direction, that's the negative direction for the voltage. This direction, as we've got it now, from left to right, gives a positive voltage. Going the other direction would reduce that positive voltage, and it could eventually make it negative. Okay. Now here's another reaction that involves a gaseous electrode. Let's look at the salt bridge again, and then we'll decide what reaction is being expressed by this. Well, this one's pretty easy. The reduction is on the right. So we're reducing copper plus 2 to copper metal. That means copper plus 2 is a reactant and copper metal is a product. If we look over here, I'm looking at hydrogen going from 0, H2 going from 0 to hydrogen ion plus 1. So goes from 0 to plus 1. That then is an oxidation, and it does belong on the left. Now, neither hydrogen nor hydrogen ion themselves can have a wire attached to them. So if you can't connect a wire to it, you have to have something that you can. And that's where the platinum electrode comes in. In that electrode, we'd have a platinum electrode wire, or something going into the solution. It would be solid. It would be in a different phase from the hydrogen, which would be gaseous. And gaseous hydrogen is in a different phase from aqueous hydrogen ion. So these separators need to be slashes, just like the one over on the right needed to be a slash. Now, so the reaction then is this one, and we are taking copper and hydrogen gas to go to copper metal plus hydrogen. And the voltage for that is plus 0.33 volts. So that does mean that copper can be reduced with hydrogen metal. So if you were to take a copper sulfate solution, according to this, at 25 degrees, and you bubbled hydrogen through it, you could reduce the copper ion to copper metal, and that reaction would be spontaneous. Voltage is positive at those concentrations. So again, let's think of the standard cell. I've got copper in one cell. That copper cell contains copper plus 2 at 1 mole per liter. The other side is a hydrogen electrode, and it's got a platinum external conductor. The hydrogen gas is bubbled into that solution around that electrode at 1 atmosphere pressure, and down in the solution, the concentration is 1 mole per liter of hydrogen ion. Now, remember, the standard cell does not depend on the balancing coefficients. And by the way, let me ask you something. When I put two reactants together and I measure a voltage for those reactions, now, when I put those two reactions together, nature doesn't know how we balance that equation. They don't know that we wrote it like I've shown you here, or if we wrote the reverse reaction. Nature doesn't know that. All it knows is the reaction is going to take place in one of those two directions. And whichever one is spontaneous will actually happen. And we have to discover whether it's the one we wrote or not. Now, let's look at what's happening here in this reaction. If I want this reaction to generate an electric current, then I want copper to, I want the copper plus 2, in this case, to be reduced. Now, how would you reduce copper plus 2? Well, you'd have to put you'd have to put electrons into that side. So I'm assuming that electrode ought to be negative if this reaction is the one that's taking place. I would set up my voltmeter that way. If I guessed right, the voltage will read positive. If I guessed wrong, though, and I attach the voltmeter the other way and just flip it over, well, then the voltmeter would read a negative voltage. Now, what does that tell me? It tells me I put the voltmeter on wrong. Nature didn't do something wrong. We did. We put the voltmeter on the wrong electrode, and we got its polarity wrong. So it's telling us the direction of the reaction is opposite to what we thought it was when we wrote down the equation. Now let's look at this one. This one is actually your lead storage battery in your car. Again, we're going to locate that salt bridge right there in the middle, and whatever we've got on the right is the reduction cell. And what we're going to do is we're going to take hydrogen, we're going to take sulfate, and what we're going to make out of it, we're going to make lead-2 dioxide, lead-2 sulfate, and lead. Those are the things that are involved. This outside electrode is lead, and we're going to stick one of our wires on that electrode. Let's look at the other side. The other side has lead, it has lead sulfate, both solids, and it has sulfate ion that's involved on that side of the reaction. So now look at the separators. Lead is a solid, lead sulfate's a solid, it's separated by a comma. That means the lead on that electrode is going to have a coating of lead sulfate on it. It's going to have sulfate ion in that solution at 1 mole per liter. And on the other side, we can look at the separators over there. Starting on the right with lead. Lead is a solid, lead sulfate is a solid, and lead dioxide is a solid. That means the lead electrode on the right side has 2 coatings on it. It has lead sulfate and lead dioxide on it. And that's all that we need to, oh, no, I'm sorry. Those solids now are separated from the other things that are aqueous. And the hydrogen ion and the sulfate ion are both in the aqueous phase. They're separated by a comma, but the aqueous phase is separated from the solid phase by the diagonal line. Okay, so let's look at the reaction that's implied with that. I'm going to take lead dioxide and the hydrogen ions, and I'm going to make lead sulfate and water out of that. So if you have a little trouble saying, well, what's oxidized? Is that oxidation or is it reduction? Well, let's back that up just a minute. I want to raise that point. What's the charge on the right? It's 0. What's the charge on the left? Well, the sulfate's -2, and we got 4 positive ions, so it's +4. So this is the reduction cell that we're showing on the right-hand side of our double line up here. And you see the reactants are lead dioxide and sulfate ion and hydrogen ion to make lead sulfate and water. There would be 2 electrons involved in that reaction. The other reaction from the other electrode is lead plus lead sulfate makes lead dioxide. And again, you can look at that and see that the charge you've got on the left is -2. The things that are shown on the right, the blue things, have no charge. So that means there are 2 electrons on the right. That is the oxidative cell, just like we said. Now, if you put in the voltages from the standard table for these 2 electrodes, and you can look them up, they are in the table, each cell of that electrode generates plus 2.04 volts. So if your 12-volt battery, you've got a 12-volt battery, you've got actually 6 of these 2-volt cells making it up if it were at standard concentrations. Okay, here's a checkpoint. Let's take a look. Write the overall balanced equation corresponding to the abbreviated cell notation. Chromium in a different phase from chromium +2 ion. that is in the oxidative cell. Lead 4 and lead plus 2 are in the reductive cell. You're going from lead 4 to lead 2. That's a reduction. And since that doesn't have a connection to the outside, we have to add platinum as the conductor. And it's in a different phase than the aqueous phase. So that's why we've got that diagonal separator there. We use the comma separator here because both of these are in the aqueous phase. We use the diagonal separator on the left because one's a solid and one's aqueous. So you were to write out the overall balanced equation. What I would do is write a reductive half cell and an oxidation half cell. Make sure we've got the same number of electrons gained and lost, and then rebalance the equation. And let me just ask you, when I balance that equation, suppose it is going to do that here. One of those is going to be a 2 electron change, the other is going to be a 3 electron change. So I'm going to have to multiply one through by 2 and the other through by 6 in order to have 6 electrons gained or lost. So when I multiply those by those coefficients, what does that do to the voltage? Wrong-o. No, it does not affect the voltage. Think about it. I'm putting 2 wires in that cell, and so when I put those 2 wires in there, it helped if my camera would turn right. When I put those 2 wires in there, does nature know how you balance that equation? Does it know you multiplied one through by 2 and the other one through by 3? Absolutely not. It generates a voltage because you have chromium in contact with 1 molar chromium ion and lead 4 in contact with lead plus 2, each at 1 molar activity or concentration. So multiplying through that equation doesn't change the voltage. The voltage is the potential difference between chromium and chromium plus 3 at 1 molar. That's what that means. So be careful. And then here's a reaction we want to do. If you do this one, you ought to do this one really, really easy, translating the other side. But what I'm going to do, first, look, there's aluminum. It's 0. Over here, aluminum's plus 3. That's one pair. And cadmium is plus 2, and cadmium is 0 here. That's the other one. So those are your 2 half cells. Practice on those and be sure you can do them. Now, I want to show you a neat thing. We talked about the free energy function. Let's review. The change in internal energy during a reaction has to do with the differences in the bonds that are broken and formed in the reactants and products. It stores the internal energy. And the internal energy doesn't always, or wouldn't necessarily always, give you a particular sign for a reaction. You can't predict what it is without doing some extra work. But it has to do with internal energy. Enthalpy has to do with heat flow when the pressure is constant. So it has to do with the way the heat from your reaction either goes to the surroundings or comes from the surroundings, depending on whether your reaction is exothermic or endothermic. So it has to do with heat flow at constant pressure. And there was a relationship between delta E and delta H. Typically, they had to do with the work involved in the reaction, but the work there was included pressure volume work. That is, if I changed the number of moles of gases of the reactants and products, I would get a heat flow that would be different depending on how the change in the heat, the number of moles of gases changed. That kind of work has to happen, but it's not extra work that you can use to run a car and run a motor or something like that. The function that has that included in it is delta G. Remember, delta G is delta H minus T delta S. And the delta H part of it had to do with the heat flow when the pressure is constant. That is one driving force. Giving off heat, distributing heat over more material is a spontaneous direction typically. Plus, there is another term, though, that is involved in that kind of delta G, the spontaneity function. It has to do with the change in entropy. Entropy disorder increases for spontaneous changes too. So delta G has both the driving force for enthalpy moving outward and the driving force for disorder moving outward, becoming more disordered. Now, the work that actually is usable is the delta G. Minus delta G is the maximum amount of work that can be done by a particular process. Now, let's look at the signs. Delta G is positive. Well, that won't happen. But if delta G is negative, that will happen. So a negative delta G times the negative out here gives me a positive amount of work. So the system can do work when delta G is negative. So delta G is minus the maximum amount of work that you can do. So if you just change the sign of delta G, that's how much work, in addition to the PV work, that reaction can carry out. Now, when you're moving charge through a potential difference, that's also a free energy. That's an energy that doesn't involve any PV work. So when I move an electron from a place of one voltage to a place of another voltage, I change its energy. And I change this form of energy, delta G. So the relationship is minus delta G is NFE, where N is the number of moles, E is the voltage for the electrode, and 96,500 coulombs per mole, that is the Faraday constant. So this represents the amount of energy that would be involved when you move 1 mole of electrons through a voltage of 1 volt. And that would give us an energy of joules. So look at what we've got. Let's take the standard condition. The standard condition, delta G superscript, then would be minus NFE0. So we can go out into our tables and measure the half cell voltages, put them together to get a standard cell voltage. We can multiply that by 96,500 and multiply it by the number of electron changes, number of moles of electrons involved. That gives us the free energy for that reaction as we have written it with N moles of electrons in that reaction. Now, remember earlier we showed that delta G superscript is minus RT log Kp. That allowed us to get the delta G value and calculate the equilibrium constant. So look at what we've got here. We can calculate the equilibrium constant, just rearrange all these things, and delta E superscript then is RT divided by NF times the log of the equilibrium constant. So the standard cell voltages can be used also to calculate equilibrium constants. So this is very, very useful. And to be honest with you, a lot of delta G's are measured from electrochemical reactions because they're really easier to measure delta G in than anything else. The others involve quite a bit of effort and work. But measuring a cell voltage is as simple as assembling the cell and connecting your voltmeter to it. So it's easy to calculate the standard free energy, and then easy also to get then the free energy change for that reaction. And that's how we put some of those values in the back of books, is by measuring the standard cell voltage to calculate the equilibrium constant. Now, the equilibrium constant for electrochemical cells uses solutions in concentration is molarity, and gas pressures are in atmospheres. So you can have a mixed equilibrium constant expression. You can write that expression down. You do have to have all liquids and solids present and things like that, but you could have some gases involved in the reaction at the same time you've got aqueous things involved in the reaction. So we wouldn't really call it a Kc or a Kp in that case, because you've got gases that need to be expressed in pressures, and you've got moles per liter, which obviously can't be expressed in pressure, but needs to be expressed in 1 mole per liter. Unit concentration is the standard. So if we take the unit concentration to be our standard state for all ions and 1 atmosphere pressure for all gases, we still write an equilibrium constant expression just like we did. Everything else works just fine. Now here's the relationship between delta G and the concentration quotient that we have at any instant during the reaction. Delta G is delta G superscript plus RT log Q. So if we go back to our earlier expression, we can put in for the delta G is minus NFE, and delta G superscript is minus NFE0, and etc. Plug those values in, and we can get this expression. This is called the Nernst equation. It gives us the voltage we would get if we change the concentrations. So the voltage would be the standard voltage minus RT over NF ln of Q, and Q now is expressed exactly like the equilibrium constant would be expressed, but using the pressures and molar concentrations that are currently in the reaction mixture. So we can use this equation to calculate the voltage of a cell that you might generate in the lab and know what the concentrations are. So the Nernst equation can be used then to calculate concentrations of ions in solution. And one of the advantages that we take of that is we build an electrode that has a hydrogen electrode. Now the hydrogen ion is what? It's going to have 1 atmosphere pressure of hydrogen gas. Around that, it's going to have 1 mole per liter hydrogen ion, and it's going to have a wire, platinum wire, sticking down into it. That would generate the hydrogen electrode at 1 molar concentration. Now, if you can, instead of doing that one, with that electrode, what we would do is build another electrode. And that electrode could be anything that we know what it is. And we could actually put that physically in the same cell with the hydrogen electrode, but come out with a different wire. And then what would happen? If I put that cell with a little thin glass membrane around it, so that it's so thin that hydrogen ions can get through it. Now, if I put that into a solution where the hydrogen ion concentration isn't 1 mole per liter, then if it's lower, the hydrogen ions in the electrode are going to migrate out. That's going to cause the voltage to change inside the electrode. If I put it in a solution and hydrogen ions is greater than 1 mole per liter, then hydrogen ions will move into the electrode, and that would change the voltage in the opposite direction. So you can calibrate that electrode to measure the pH of a solution. It measures the hydrogen electrochemical voltage first, and then internally, by computer calculations, it calculates then what the pH of that solution is. And that's how pH meters work. But you can have other important voltaic cells. There are things like the lead storage battery that we talked about already. The dry cell that you have in your flashlight is a 1.5 volt electrochemical cell. Alkaline dry cells better than the old ones that we used to use. They give more energy and give more power, but it's got a different set of concentrations of things inside it, and it's operating in an alkaline solution, whereas the other dry cell is more acidic. There's the nickel cadmium battery that you use a lot, and mercury batteries, silver oxide batteries, and fuel cells are just to name a few of them that you've used. Probably all of those except the fuel cell. That's the one that we're looking to be able to generate power from a fuel that you could burn in the air. And we've got several of them already that work. There's hydrocarbon fuel cells. Typically, the methane works reasonably well. And there's a hydrogen fuel cell that works well also. Now, let's look at some more problems. Here's again, locate our double line. Means reduction is on the right, and it's showing zinc +2 being reduced to zinc metal. On the left side of that, we have hydrogen and hydroxide. This is going to be an alkaline reaction. And we're going to have hydrogen and hydroxide. Hydrogen is gaseous, hydroxide is aqueous. The separator needs to be a slash. And the external connector has to be a metal that's unreactive in these solutions. So platinum is what we typically use. And it's solid, it's in a separate phase from the gaseous hydrogen. So we're going to have a hydrogen electrode on this side, but instead of having hydrogen ion, it's going to have hydroxide ion present at 1 mole per liter. The zinc metal is going to be in a solution of zinc ion at 1 mole per liter. And write the oxidative or anode reaction for that one. And now we know reduction's on the right. We know this is oxidation. So we're going to have hydrogen and hydroxide involved in that reaction. Oxidation is the anode of the reaction. And here's the oxidation cell. We've got hydrogen reacting with hydroxide. It's going to make water. And there's 2 negative charges on the left. So we need 2 electrons on the right to balance charge. So that's the anode cell where oxidation takes place. Now, what's the voltage of that cell? What's the sign of the voltage? Remember, electrons can't go out into the solution. Electrons have to stay on the electrode. So the oxidative cell is the one that keeps the electrons, the electrons. That's going to be the platinum wire. The platinum wire here is going to be the negative electrode. Now, the E0 for this cell from the book, this is oxidation. So it's negative of the value that's shown in the book. Remember, the book shows reduction potentials. So if you look this one up, you get negative 0.83. But this is now an oxidative cell, so I need to change the sign of the reduction potential. So this cell then is going to be a positive voltage. Reduction occurs at the cathode, and of course, that one's pretty easy to spot. Zinc +2 electrons reduces to zinc ion, and 2 electrons zinc reduces to zinc metal. And if you look up that voltage in the book as a reduction potential, written exactly the way it is 0.763 negative. Now, this is a reduction cell, so the sign out front is positive. It is the same sign as the table value, whereas the one up above is opposite direction of the table values. They're all reduction. So it's the negative of the reduction potential, and that sign was negative. So if I put these two together, I get the overall cell reaction is going to be hydrogen and 2 hydroxides and two zinc ions go to water and zinc metal. And the voltage for that would be the standard voltage. We get from the first value, we get 0.83. It's going to be positive. The second value, 0.763, is negative. When I subtract the two together, the voltage is plus 0.063 volts. Okay, it's not very much voltage, but now what does that tell me about this reaction? That's right. It's spontaneous because the voltage is positive. Now, it's spontaneous when? When I've got hydrogen at 1 atmosphere pressure in connection to a platinum electrode in a solution that has 0.1 molar hydroxide ion in one cell. My other cell, I'm going to have a zinc electrode. The zinc is going to, zinc ion in that solution is going to be at 1 mole per liter. And connect them with a salt bridge and et cetera, et cetera. That reaction, the way it's written, is spontaneous at those concentrations. Okay, look at the overall reaction. What if I added acid to that? Okay, the acid is going to react with a hydroxide. The hydroxide is a reactant. I need more reactant, not less, to push it to the right. So if I take away some of the hydroxide ion, Le Chatellier says it'll shift to the left. That's going to be in the opposite direction to the voltage we got. So it's going to reduce the voltage, become less negative, or less positive rather, and wouldn't take it far, wouldn't take much to get it going the other direction, would it? Okay. Now, we can calculate the equilibrium constant for this reaction because we know these values. The log of the equilibrium constant, the number of electrons transferred. Now be careful here. We're talking about the equilibrium constant for an overall reaction. So that means we have to have the total number of electrons that was canceled out up here. In this case, it was 2 and 2 is not a biggie. But if I had to multiply this first one through by 3 and the second one through by 2, it would be 6 moles of electrons that was canceled out. Not either 3 or 2. It would be 6. Oh, that's probably B or C on the exam. Be careful. All right, so there's my numbers. Remember the value of R you have to use when you're using energy is 8.314. You have to have all your energy units in joules, and that's what we've got when we got coulombs times volts is joules. Okay, and there we get the log of the equilibrium constant, and then the equilibrium constant, if I take E to the 4.9076, I get 135. So that's the equilibrium constant then for that reaction. Okay. Calculate the cell voltage if the pressure of hydrogen ion is 300 torr, the pH is 8, and the zinc concentration is 1 mole per liter. These are all typical calculation numbers we might actually have. Okay, it's the Nernst equation. The E is the E0 minus RT over NF log Q. So there is my standard voltage. I calculate up here, 0.063 minus R T over NF. Now, RT over NF at 25 degrees, the Faraday, R was 8.314, the temperature is 298 Kelvin, the Faraday constant is 96,500. You plug all those numbers in, you get 0.0591, and then N is going to be 2 electrons transferred. And then if I'm looking at my overall reaction up here, there's nothing on the right whose concentration can change, so the product is a 1. The pressure of the O2 is here, and the molar concentration of hydroxide ion is squared, and the zinc concentration is to the first power. Those are the things in the reaction. You see, they're mixed. Hydrogen is gas, it should be expressed in atmospheres of pressure. Hydroxide is aqueous, it has to be in moles per liter, and there's 2 of them, so we square it. Zinc is moles per liter, there's just 1, so we don't need to do anything to it. I can plug in my numbers now and get my calculation, and I get the voltages now minus 0.083. Now, remember I put in all of the numbers in their appropriate unit that we had from up above. And now it is kind of interesting, isn't it? The value now is negative. What did that tell me? You're right. It doesn't go the direction I wrote it. It does what it does. We're going to get a negative voltage if we hook the electrode up the way we thought we were going to. If we thought one of the electrodes was negative and we put the negative terminal of the voltmeter on that one and the positive one on the other one and measure the voltage, we get negative, which told us that, hey, we have the reaction going the wrong direction. It still happens, but it's not the one we've written here. It's the reverse of it. And of course, if you reversed it, it would give a positive 0.84 volts if we wrote the reaction the other direction. Let's go back here. All right, here's another one. Here's some cell voltage given to you, and here's a reaction, calculated voltage, not the standard voltage of the electrochemical cell shown here. And if you'll notice, I've got little subscripts by these things to represent molarity. It's actually called activity. And it's in dilute solutions, the activity and the concentration are the same. Now, when you get to quant, they'll really hammer on the difference between molar concentration and molar activity. Activity is the effective concentration. And you see, when you have ions present in solution, they're not independent of each other. There's a positive one, and somewhere there's a negative one. And those ions attract each other. And negative ones repel each other. Positive ones and positive ones attract each other. So in the solution, there will be regions where you might have, for some crazy reason, just happen to have a bunch of positive ions together. And there might be a cluster of negative ions in some volume somewhere else in the solution. So as soon as you get a concentration above 0, those ions start to interact with each other. And if you got them high enough, you could even start to form ion pairs in the solution. And so the concentration of each of those individual ions would go down because of these ion pairs that form. And it might not even be a pairing of an ion that's participating in the reaction. It might be, maybe you've got sodium nitrate in the solution to act as an electrolyte to help it conduct an electric current, but it's not involved in the reaction at all. Well, it does affect the concentration of anything that's present. So it's called activity, takes that into account. It's the effective concentration of cadmium ion is going to be 3.2 molar. And be careful now, the effective concentration of nitrate is going to be twice that. It's going to be 6.4 molar. There's 2 of them. Okay, so that's the difference between activity and concentration. I need to mention it here. You need to be aware of it here in Gen Chem 2. They will really emphasize it in quant. Okay, that's going to finish this up, and it's coming out just about right. And this is my dream for you, that your dreams and plans for your future will come to pass just as you imagine them. And may God bless you and cause that to happen. So with that said, we will end effectively Gen Chem 2. We will have Friday to do some review, and we will